Okay, so we're gonna go with LC and BT. Hmm, hard question. Okay, it's medium in LeetCode. So given a tree, find the lowest common ancestor of the given nodes. According to the definition of LCA, the lowest common ancestor is defined between two nodes as the lowest node that has both at its descendant. So basically for 5 and 1, that's 3. Okay. Hmm. For 5 and 4, it is 5 only. Yeah. Okay, how do we do it? Hmm. Supposed to return a tree node. Okay. We do a traversal and we get it. No, in the traversal zone. How do we return back? How do uh, how do we get a return back? Like 5 parent is 1, parent is 4, like that. Okay, 5 and 1 have the parent as 3. Hmm. How do you find the parent efficiently? Hmm. Okay, how do we find the parent? Okay. The lowest common ancestor of nodes. There is some logic to it. The lowest common ancestor of 5 and 4. Hmm. How do we do it? Let me start a timer. We'll know. Hmm. Till now, I have learned all about printing root to leaf, which I did a traversal of in order traversal. So here also I can do a traversal. What if we do a traversal from 5? No, how do we do a traversal from parent node? We do a traversal from parent node in two different directions. There should be a function which can tell me the parent of anyone. So the time complexity expected. No, that we are all not learning peanut execute and q exists in the tree and number of values 10 to the 5 for n log n. So how do we get n log n value from both of it? Hmm. What if everything has a level value attached to it? Let's suppose it is level 0, 1, 2, 3. So level 3 and level 1. So you know what? Let me get the level of both. And the level of 0 is minus 1. Level 0, level 1. So let me traverse in the whole route and do we traverse and get the level of both? And both have the same level. So obviously they will have the lowest common ancestor in Traversal, but how do we find the ancestor still? There needs to be an intuition for this, right? Hmm. Okay, we'll be thinking for 4 to 5 minutes. If we can't find out even anything, we'll try to find other ways. find the lowest. No, man, it's really important. I don't know what to do. Just to find between two nodes, such as so suppose if you find the parent of a node, parent of 5 is 3, parent of 1 is 2. Just keep going until you find a common parent. That is what I would have thought of. Like find if until they are on the same level, they're not the same level, just keep going. There has to be something right. What if we have a list from root till like for 5 we have till leaf till parent till leaf. Okay, the path of 5. Same goes for 1. We have for 1. And the moment the paths converge, suppose this is this and this is this. Oh yeah, we can do this. We can do in order traversal. We can do in order traversal of it. That can be good. We can have a path of the in order traversal, but it expects me to have a tree node. A vector of tree node value. The moment you get this, you have to turn it. Hmm. How do you get that? How do you get the parent of it? We have what is left, right, and that's all. Yes, has been 6 minutes, and I can't even know. So start is checking if the current node is null or matches one of the target. If the route is null or matched by the target, then the route to be okay. I formally passive search in the left tree to find. Hmm. I don't know. Hmm. What does it even mean by recursive search? So start by checking if the current node is null or matches one of the target nodes. If the root is null or matches other nodes, turn the root as it could be the LCA or simply indicate the end of the search path. Perform a recursive search in the left subtree to find nodes. Action while we're calling and then the right. Hmm. Yeah. Okay, I understood. He's probably going from root and he's searching everywhere. The moment he finds one of those, we should go for it. Same goes for right and keep searching for it. Hmm. Okay. And we need, you know what? I think I have a solution which will be taking probably more time complexity. Okay. We search, we traverse, and the moment we reach it, That's what I'm thinking. I know the traversal of it, part of it. So we can traverse 3, 5, 2, 4. The moment we get 5, we will turn in the path of 3 and 5. Hmm. I'm still confused over it. We had a left call and a right call. For the moment after Navera. Hmm. You go right, you call to left, you call to right. You call to left, you call to right. Hmm. Let's try. We'll call a function called LCA. I will be passing road left PQ. Hmm. I mean the path to be saved in the value. So vector of tree node star. You know what? Vector of tree node star. 320, 312. Hmm. Hmm. So we're going to do a traversal here. So suppose if root is null, we'll just return. And we want the changes to be done in the real time. So if row dot val is equals to p dot val or row dot val is equals to q dot val, though. So hmm. So the moment these two are there, what we'll be doing is we'll be pushing into left dot push back or row dot val and return. Otherwise, or return. Otherwise, I don't know what to do. Should we, like, how do we know after this also, after this traversal, we should be keeping it? Oh, the moment we get this, we should be stopping the traversal, right? Hmm. Hmm. Okay. How do you push it? How do you push it? How do you push it into, like, how do you know you have to stop? Like the moment we reach this 5, okay, but it was still going in the left side. I'll be calling the function. To root left, P, Q, and left. Same goes for root right, P, Q, left. How does it know it has to be stopped? Hmm. What should we return? Hmm. I don't know. Okay, I'm just missing the part of how do we know when to stop. Basically, I need a vector of these two. That's all. If we get a list of these two, hmm. Suppose if we get this for 2 and 8, this should have returned 3. But then you have to compare. So this 2 returns is being returned by the function. No, this 5 is being returned. Not. It's root null. I'll just try to do the brute force part. If root dot left is null, root dot right is null return. No, I don't think so. What do we do? I'm still confused. Hmm. If both recursive calls return valid means of one target node was found in each subject space, the parent node root number with LCA, which if only one of the subreturns are not in, it implies both target nodes are the in subset. Return the non-null result, which represents I'm confused. If root is null or root is p or root is q. Oh yeah, it's not value, it's comparison. So return the root. Otherwise, what we do is we search in the left and the right. If left was null, admit on right. If right or null, otherwise then root. What do you mean? That's all? How do you? That's all. What the? Hmm. So you don't need a proper function. You just call that again. So if what the hell? If root is null, uh, root is equals to p and root is equals to q. Return root. Anti-left, not anti-left. 3. Node star left is equals to lowest common ancestor of root left p. Q. So how does it work? Like if left is equals to null, return right. And if right is equals to null, return left. Return group. Needs to be something. I think there is this part. Oh yeah, wait. So how does it work? Basically, it is going to be called in the left and the right just because it searches, and the moment you get any of it, you're returning the value, right? So for this function, so suppose we were searching 2, 5, 6, not we got a null value. We got null value from here. We got a 2 value from there. So 2 came to this person. For this person, 2 came. For this person, he went here and 1. For him, 1 came. I don't know. I'm still confused. Is this supposed to be right? How? Uh, uh, Half sure. What the hell? That's all. Something is supposed to be not. Let me see how although.
So before starting off this video, I'd love to thank Reliable for so if I draw the path between them, so this guy will become the lowest common ancestor because out of all the ancestor, this is the one, the node 4 ancestor. So let's common ancestor. Econ startups, what do you need to do? And you will be hired. And the best thing about this is the relevant tests are free and you can check out all the links in the description below. Doing extremely well. So today we will be solving the problem, finding the lowest common ancestor in a binary tree. So assume this is the binary tree that is given to you, right? And you have to find the lowest common ancestor. So let's understand what is lowest common ancestor. So if I consider the nodes 4 and 7, okay. So where is the node 4? Here is the node 4. Here is the node 7, okay. And if I talk about the ancestors, 7's ancestor is 5, and then 2, and then 1. So I can say 7's ancestor is 5 to 1. If I talk about 4's ancestor, it's 2 and 1. So the guy who is at the deepest level is basically known as the lowest common ancestor. So if I draw the path between them, so this guy will become the one which is at the lowest common ancestor.
Okay.
So can I say this common ancestor will be your lowest common ancestor. So basically the path will be node 2 itself is an 4 and from the root. And if I write the path, it's going to be 1. Perfect. That's the second element. Again, 2 and 2 are matching. This is the third. They do not match. Element that matched was 2 and 2. So whichever is the last element that matched, so some data structure. So a time complexity of big O of n go of n, then the space complexity of big O of n. Complexity of big O of n. The paths. Time complex. We have to improve the space complexity. Assuming I'm looking for the LCA of the node 4 and node 7. So you're going to follow a traversal technique, okay? And that traversal technique will be the recursive traversal technique where we move left and where we move right. Basically, the DFS traversal is what we are going to follow. So what we initially will do is we'll start the DFS traversal. We will be over here. You know, it has to go to the left and it has to go to the right. So first it will go to the left. We go to the left. Then again we know that it will go to the left. So we go to the left. Now remember, the moment I repeat, the moment you reach a node which is a part of your node 4 or which is one of the nodes that you're looking for, what you will do is you will, instead of going further left and right, you will return 4 from that part. I repeat, you will return 4 from that part. So the left give you 4. Now it's time to go to the right. So what you'll do is you'll go to the right. So that's over here. From here, the left give you 4, and it's time to go to the right. So when you go to the right, 5 is not what you're looking for. So you will go to the left. Okay. Goes to the left, finds a null. So a null. What you'll do is you will null. Okay. Now you find some no further need of going to the left. Now the 5, 7. Remember, what this signifies is it's not a null that you'll take. So this guy will take 7. So if it's a null, you're gonna take the other one. If this guy is a null, you're gonna take the other one. Okay. So now we are coming across to 2. For the guy 2, from the left, you're getting 4. From the right, you're getting 6. Why did you return 4? Because you actually figured out 4. Why did you return 7? Because if there was a case when you're not on the left, there was actually signifies that both the nodes under you, can I say this guy is the LCA over here, hence I return 2. So if both the guys left guy returns 2, so I'll go to the right.
I understood. Basically, what works is in the middle of the recursion. Okay, the code was working in the middle of the recursion. So in the middle of it, when this part, suppose this guy has searched 7 4, and this was in the middle of it, it found left was null. Like for him, left got null, and the right also got null. So that means he understood 2, and so 2 was returned to him. Okay, that is why. Okay, I mean, needs some understanding. It's kind of tough, but okay. Okay, now the question is, given the root of a tree, return the maximum width of the given tree. So the maximum width of a tree is the maximum width among all its levels. So basically, the width of a tree is defined as the length between the end nodes, the leftmost and rightmost. So isn't this just a BFS with a, I don't know, like, okay, the maximum width is 4, which is exists in the third level. So basically 5, 3, null, 9. Wait a minute, there's null, right? So how come it's a width? So the maximum width is exists in the fourth level, which is 6 null, and then there is null, null, and then there is a null, null, and 7. What do you mean? I'm confused. Okay. And so how come there's not a null being counted? So basically the width of a tree is defined as the length between the end nodes, the leftmost and rightmost, with a full null node between the end nodes that would be present in complementary extending down to that level also counted in the length calculation. Okay, fine. Fair enough. So every null value should be replaced with a -1 value. Okay. I see. What can we do this that the number of nodes in the range and the okay, it is brute force. What I'll do is I'll first know the number of levels they have and then I can do it. Okay. Last level basically. It is always guaranteed that the last level will be that level. So I just need to know the number of levels they have. There's a function which I calculated called height of a binary tree. You can use that. Maximum depth. Yeah, I can use the function from here. So basically, it figured out 3 because 1, 2, 3. You can use that. Hmm. I'm just trying to reuse the code. So it's just count if root is null, return 0. Not return 0. If root is null, that means there has nothing, so I will return 0. There's a queue, it will be pushing into that queue. While the queue is not empty, we take a size of the queue, we pop, it goes, count, plus, plus. So basically, count is the depth of that binary tree. So now what we need to do is, and temp count is equal to 0, and q3 node star q. Okay, we can create a new tree node, right? Q2, q so q2 dot push root. We have pushed the root, and while q2 is not empty, or it is not empty, what we need to do is we need to find the size of it, and and if temp count is equals to, what if we increase the temp count right now? Temp count is 0, right? No, the depth is 1, 2, 3. The depth is 3. So if temp count plus plus, if temp count is equals to count, we'll do a special traversal. Else, I think it's going to be a lot of redundancy in the code, but I think we can do it. Okay, how do we do it? If temp count gets equal to count, the moment both of it becomes equal. If temp count equals to count, we'll be creating a count called answer anyways. So we have answer variable already? No, we don't have. And we want to return answer anyways. So, what we need to do is we need to create a tree node start temp. You know what? The same thing. Tree node temp is equals to q2 dot front, q2 dot front, and we'll be popping in q2. Dot pop, and now what we need to do is now if temp dot left is equals to null. If temp dot left is, we need to create a full binary tree basically, I guess. Okay, so if temp dot left is equals to null, then q should have push back new tree node The value of minus 1. If temp count equals to return size. Can return size? What do you mean by if pushback and standard? You know what? We'll create a tree node. Tree node. New is equals to new value. Q2 dot pushback. New value. Let's see if it works. Okay, Q2 is pushback. Oh, wait. We don't have pushback included. We have dot push. So the error was never about that. Error was about the syntax. My bad. Okay. Let's see. Okay, it is not correct because 0 is being returned here. The reason is the Q2 is not empty. But the Q2 size. And we haven't ran a loop till that value. So this how it would happen is for I into I equals 0, I less than size, I plus plus. I guess this should do the job. Now the iterations are being run and still it is becoming 0 because okay, temp count. You know what? Let me see how the temp count goes. 3 out of temp count. Comment underline. Okay, temp count only goes till 1. And the reason is because I size if temp of left is null, we are gonna push the value of new value there. It is again null. So yeah, the iteration should go right. If temp dot left is null, if temp dot right is null. Never reiterated. The reason is the loop never reiterated. Why is that so? I'm wondering. Okay, I think the reason why it was not working was because I was not considering the case of not null. Yeah. Okay, I think this question can be done. I just need to do the part of when the last level. Hmm. Let's try this. So what we're gonna do is we are gonna try for if okay. See, the reason is the even in this case the -1 was also counted, so we should go from here to here. I hope the edge one is correct. Hmm. Okay, I have a theory that I think there might be a case where 6 and 7 comes in this part of it. Oh, sorry for the interruption. So my thing is, I think there might be a situation where this 6 and 7 comes here, but this would be only this much length, and this length would be high, so I can't be just calculating with. No, I don't even need this height. I just need to populate it with minus 1, minus 1, minus 1. Yeah, I don't need this. I don't need the logic. I don't need the logic of temp count, basically. We will be populating it with minus 1 every time. We don't need a if and else condition. So that leaves us to. Okay, this is the if and the else part of it. This is a for loop. Okay, huh? Now we need to calculate the distance for every route. So the initial value will be obviously 1. So we'll be populating the answer with 1. Now the thing is, if route is null, return 0. Hmm. Now, if, okay, so we need to calculate the distance between these two, right? How do we know? Suppose the 7 was here. How do we know that there won't be any minus 1? We can push it and save the value, right? Hmm. We can create a vector. Level. And we'll be pushing in the level 10. Oh, yeah, I have got an idea. We'll be pushing to the level temp dot val and will be what? It's a very brute force method, but it works. Int right is equals to level dot size minus 1 while level right is equals to minus 1 right minus minus and answer is equals to max of answer comma right. And return answer. I think this works. Basically, we store all the values, and while the minus 1 was there, we move back, and we don't need a temp counter, obviously. I hope this works. This logic seems very. Unless TLE happens in this. TLE won't happen, but in this input size, I guess. Hmm. There is an addition of offset in the line. Which line? Okay, there is some. Just there is some. I don't know. Level is an integer considering variable, right? We are iterating to size. So Q2. Q2 has pushed to this Q2 the pop. Double pushback temp value. If temp, the value is left as null, so we're creating a new figure of minus one and we're pushing it if and else in the Q2 we'll be pushing the left node. If the right is null, we'll be pushing the value of new value there and we'll be pushing temp right. Okay, that is the number of iterations. Anti-right is equals to level dot size minus 1. So while level indexed with right is equals to minus 1, we need to decrease the right value. I need to make sure right is greater than 0. I can only think of one place right is inside. Oh wait, there's a memory limit exceeding now because I think a number of we create a vector of int for every value is right. So what is the memory exceeding in this? Hmm. Why don't we store every level in this and then we'll be just iterating? We are basically doing that only, if I'm not wrong. We're just storing for every level. So what one, two, three levels only. Three three levels it counts to. For anti I equals 0, I less than size, I plus plus tray node start temp is equals to q to the front value and then q to pop level that pushback temp value. If temp left is null, tray node new value. I don't know what is wrong. If anti right is equals to I'm confused. What is going on here? If temp right is null, then we will be getting this value and due to that positional value. Okay. Why is there a memory limit exceeding? I don't know. I have to take hint. I have no idea why memory is exceeding. Probably something I'm doing wrong. ChatGPT. Why is there a memory limit exceeding? Okay. Memory exceeded because of this part. If temp of left is null, then what we're gonna do? So similar to that, so what happens? Suppose you reach a leaf node, and suppose you're null, so you create this, and the moment. Okay, we need to only iterate. Okay, we need to only iterate till. Need to. Oh, we need a depth function then. We need the depth function value then. Depth count is a value of depth. So this is the value we're having a count, and the answer is 1, and we won't be running it till it's empty. We'll be running it till and here equals to I less than count I plus plus. I think it should work. Okay, answer is 3 because I think right, because it's always indexed, human indexed. Oh, I mean this won't have a very good time complexity, but it will work good. Wait, you know what? It won't even work. Fair enough. There's another issue. It's a level is this, uh, not right. Level is okay. Understood one more thing. And right left is equals to 0, and while left greater less left greater than less than level dot size, and level of left is equals to -1, left plus plus, and it should be right minus left plus 1. Does this work? I hope it does. Yeah, that's all. I mean, I never thought about the part that I thought they were only considering. So basically, it's width and actual width. Now we have memory limit exceeded, which I don't know how to go around. So I have done my part. Oh, there's a memory limit exceeding part. So now we need to see what genius push logic they have thought about it. So basically, to determine the maximum width, an effective strategy would be assign and identify indexes for the leftmost and rightmost nodes at each level. So using these indexes, we can calculate width for each level with subtracting the index that obviously. Start by assigning an index to the root node 0 for each level. The left node gets a value of the left node. Use BFS and track each node's position as if they were a complete binary tree for each level in the node. Note the position of the first and last node and compute the difference. Yeah, that's what even I'm doing, right? Level 2 level. Yeah, okay. Even I'm doing that. So what is the difference? What did he do? It's obviously max width, so each element is a pair of curate push. So it's not empty, get a number of size, cube, minimum index push. Show the index of the first node at this level. Okay, I think let me just ask one more thing to this. Why is this getting No. You know some of obviously. So let's say the first tree. Oh, okay. So in general, after the queue size becomes 2 to the power k. The tree height is 30. Yeah. Okay, makes sense. So what do we do? Which comes in the tens of bytes of far beyond the limit. So there's another bug. Suppose your original tree is this. Okay, so how do we fix that? That is when we use this his idea, which is if it is not root, if root is empty, return 0, obviously. If initialize max is 0, it's element is the pair of node and its index. What is the index? So, each node is a pair of the node and its index. So push the root node with the index of 0, and while it's not empty, we get the size, we get the minimum index, the value of show the index of the first node at this level. Initialize variables to first, track first and last index. So basically first and last is 0. So traverse all along it and get the current index from the minimum index. Tree node right is equal. Tree node equals to q dot front dot first. First is the node, second is the value of index. Okay, it's basically a temp value which we take. Pop the no q, and if did we pop the q always? We have always popped the q. Oh, but limit exceeds a lot. If I is equals to 0, that means that the bit of if I, which is the I part of it, this is the first node. If it is the first node, then first is equals to current index. If I is equals to S, then last equals to current index. If the left child exists, then push the value 2 into current index plus 1. Right child exists 2 into current index plus 2. Okay, understood. Understood on some levels. Basically, the index of the left is the index. Suppose index is 0, this becomes 1. This becomes 1 into 2, 2 plus 1, 3. This becomes 1 into 2 plus, okay, this becomes 1, becomes 2. Hmm. Oh, yeah, makes sense. I mean, at the end of the day, yeah. This will go 1, 2, 3, 4, 5, 6, 7. Yeah, yeah, works. 1, 2, 3, 4, 5. So this is 1, 2, 0, 1, 2, 3, 4. So 0, 1, 2, 3, 4. This is 4. And so how would this would have been a 4? 0, 1 into 2 plus 2. Yeah, makes sense. Makes sense. Makes sense. Totally makes sense. Okay, yeah, yeah. Hmm. Okay, I'll do that. That I'll do in the next stream because I'm a little tired for today. But I understood the part of it. Yeah, basically we're just gonna do the normal indexing. Makes sense. Yeah. Okay, that is enough for today, I guess.